Hello, class. Now we have seen the Black-Scholes-Mertens partial differential equation for a derivative asset with a underlying stock that pays no dividends. So we have a functional form here. Now, how are we gonna get the value of f? Right, so we have to solve this partial differential equation. In order to solve a partial differential equation, you would need some boundary conditions. So we have to know, what that f is. So if we have a European call option, that means the derivative asset f must follow a boundary condition where at the maturity date of the option, the price or the payoff of the derivative asset must be like this. So if the stock price at maturity date is greater than the strike price, the value of the option, the call, is then ST, the price of stock at maturity minus the strike price. If the stock price at maturity is smaller than the strike price, then the value of the call is 0. So at no point in time at the maturity date, or actually for that matter, anytime before the maturity date, the value of the call cannot be negative. So it's always going to be positive. That's where we have this max function here. Now, so this forms the boundary condition. So once you have the boundary condition, you can solve the partial differential equation here and to derive what the call value is. Now, in this case, because the stock price follows a normal process, and we are able to derive a closed form solution for the call. Now, in a subsequent lecture, we're gonna talk about or actually derive this formula here based on an approach from Richard Feynman and Mark Catt. It's actually interesting that we obtain something from in finance based on some results by physicists. So here, let's say we have already derived that. We have this particular functional form for this call price. And you can see that this is a functional form that links the call price with the price of the underlying variable and plus some other parameters like the strike price, the interest rate, the time to maturity, and so on and so forth, and the volatility and so on, right? So we basically have a functional form that as soon as we know those parameters, we can obtain the price. Now, we have a normal distribution here, cumulative normal. So we have this ND1, and D1 has a form like this, and D2 has a form like that. Now, so basically, if we know a whole bunch of things like stock price, strike, interest rate, volatility, and the time to maturity. So basically 1, 2, 3, 4, 5. So if we know those 5 values, then we're able to obtain the price of the call. Now, okay, so we have obtained the price of the call in a very involved way by needing to solve a partial differential equation. But once we have done this, the price of a put, a related put, is actually very easily derived. So, you don't have to go through solving a partial differential equation to obtain the price of a put. So anybody can really do it. So how are we going to do that? Well, so what you need is you need a put call parity condition, which links the call with the put. And you just also going to make use of a simple identity here. Now, so basically from the put call parity, we have this, the call price plus the strike price, K times e to the power minus RT. R is the risk-free rate of return annualized, and it's equal to the put price plus the initial price of the stock. Okay, so now with this put call parity, you just substitute in the formula for the call, which is this part here. Okay, then plus K times e to the power minus RT minus S naught. Okay, then you take the common factor S naught and K times e to the power minus RT here. So you will get this part here. Now rearrange a little bit. So put in the negative sign inside. So this becomes positive and this becomes 1 minus. Do the same thing for here. Then now you have 1 minus ND2. You can actually then use this particular identity here. 1 minus NX is equal to N minus X. So you get K times e to the power minus RT and minus D2 minus S naught times N minus D1. So now through this simple derivation, you are able then derive the price for a European call, a European put that with the underlying asset that doesn't pay dividend. So it's this derivation itself is rather simple to have.